Okay, here we go. All right, so this is the second video in which we are finishing up the Exam 3 review, picking up where we left off in class. In class, we did questions 1 and 2, and we just have questions 3 and 4 left to do. So, number 3. Suppose that each person in a random sample of 48 male students and in a random sample of 91 female students at a particular college was classified according to gender and whether they usually or rarely eat 3 meals a day. The data from the samples were organized as follows. So you have male, female, and then they usually eat 3 meals a day or rarely eat 3 meals a day, and then the data for each of them. At a 5% level of significance, test the claim that the distribution of population proportions for gender is not the same for each response. So we have 4 options, right? We have ANOVA, chi-squared for goodness of fit, chi-squared for independence, or chi-squared for homogeneity.
Homogeneity.
Yeah, homogeneity. Which of the 4 is it?
I say homogeneity. The proportions, population proportions.
Chi-square for homogeneity.
Because it says gender and stuff.
The reason is because we have 2 different populations. They did 2 different samples, right? So that could be an indicator. Notice how one of the populations was males, from which they took a sample from, and a different population was females that they took a sample from. And then if you look at the toolkit sheet we made today, the only one that's categorical across multiple populations is the homogeneity.
Oh, that's in one population. Oh.
So, part A. What are the null and alternative hypotheses? Let me see if I can zoom in a little bit, make more space for myself. Okay, so first the null. So the null is the distribution of, I guess I could say, I'm just going to call the usually eat 3 meals a day or rarely eat 3 meals a day, I'm going to call that the responses. Okay, the distribution of responses is the same for each gender. The gender options being male and female. Then the alternative is the exact same wording, except saying the same, we say are not the same, right? So the distribution of responses, being that they usually eat 3 meals a day or rarely eat 3 meals a day, is not the same for each gender.
What if we said outcomes?
Read it to me in a sentence.
The distributions of outcomes is the same for each gender, or the distributions of outcomes is not the same.
I'd like, in place of the word outcomes, I'd like it to be more in context of the problem. Yeah. And in this case, responses, because they're responding. Yeah. Any other questions here? Okay, part B. Using your calculator, fill in the expected frequencies table below. Are the criteria for chi-square distribution met? Round to 3 decimal places. And then let's just keep in mind what the next part will be. The next part is asking us to find the test statistic, degrees of freedom, and p-value, because we're actually going to be able to find all of these in one go. So, we go to our calculators. We do second matrix. Go over to edit. We are editing matrix A. How many rows by how many columns is this? 2 by 2. 2 rows by 2 columns. So 2 by 2.
Excuse me, are we rounding our test statistic p-value and everything to 3 as well?
Yes, let's go to 3 decimal places. So remember, in matrix A, you enter in the original observed data. So that's 22, 26, 54, and 37. So then we go to stat, tests, go up to the chi-square test. You have to hit enter a few times. Oops, it did not work quite how I wanted. Let me redo that. So stat, tests, chi-square test. Enter, enter, enter. Calculate. Okay. And it gives us the following results. I'm going to come back to part B. Okay, I'm going to come back to part B. I'm going to go ahead to part C because in your calculators at this point in time, you should have the test statistic, degrees of freedom, and p-value. So your test statistic should be 2.314. Degrees of freedom is 1. And the p-value is 0.128.
How about something different?
Something different?
Yeah.
Let me take a look. Now's the time to ask for help with your calculators, guys.
That's what I thought.
Oh, it was 54, not 55.
Oh.
Any other questions? Okay, so I have that info. Let's go ahead and jump back to part B for the expected frequencies. To do so, you go back to your matrix. So we're going to do second matrix. Go over to edit. And our expected frequencies are in which matrix? B. So let's go down to B. And you should get the following. We said we go to 3 decimal places. So 26.245. I'm going to go horizontally. 21.755. 49.755. And lastly, 41.245.
A whole lot easier when it's 2 by 2.
Yeah. Pretty nice. And so are the criteria for the chi-square distribution met?
Yes.
Yes. Why?
Expected frequencies are
At least all
greater
5
than
and 5.
Yeah. Because
5.
all expected frequencies or expected values
Is it at least 5, greater than 5?
greater than 5.
I said it was a 10.
That was in the previous chapter when we were working. Oh gosh, I'm trying to blink here. Which chapter was that even?
When it was like hypothesis testing.
It was hypothesis testing of quantitative data. Ooh, that's when we did it for 10.
So when it's like when it's regarding like chi-square and all this stuff, no, it's always greater.
It's
than
5, yeah. Yeah, good question. Any other questions up to here?
Yeah, my bad. How did you get those numbers
Which ones?
in the chart? Those.
Oh, these ones here?
Yes.
So you have to go back to your matrix. So go to second matrix. Go over to edit. Go down to matrix B. So the expected values are always in matrix B. Yeah, so matrix A is where you input your data, then do the chi-square test. Once that's done, when you go back into matrix B, it will be updated with your expected values.
So, like, on the tests, like, do you suggest to do, like, the test statistic, degrees of freedom, and the p-value first?
Yeah.
And then go back?
Yeah,
to the-
I would recommend that just because it's on your calculator already. It's like, oh, might as well just fill in this information while it's on my screen and then go back. But you don't have to. You could do this first and then redo the chi-square test again for a second time to get this information populated on your screen.
Thank you.
All right. So now what conclusions can you make about the null and alternative hypotheses? Well, the p-value is 12.8% compared to our level of significance, which is 5%. Is 12.8% less than 5%? No, that is not a true statement. Therefore, it is not statistically significant. So we do not reject the null and do not support the alternative. And lastly, we can now state our conclusion in the context of the problem. So at the 5% significance level, the sample data do not support the claim. Do not support the claim that the distribution of responses I'm just going to put in parentheses 3 meals a day, right? Because that's what the responses were in terms of. So distribution of responses, talking about the 3 meals a day, is not the same for each gender. Where in the context of this problem, male, female. Or something along those lines. Again, some of you guys might phrase it a little bit differently, but so long as you have 5% significance level, sample data do not support the claim being what your alternative hypothesis was.
Would we mark them correct if we didn't put for each gender?
For each gender, yeah, you would lose some points. You would need to say for the same for each gender. Yeah.
So little things like that, like we have to watch out.
Yeah. Yeah.
So I don't understand. Like, so in part D, we're basically accepting the null hypothesis, but in part E, we're kind of going the opposite on that. We're not supporting it because
We are not supporting the alternative. So whenever we've done our overall, and there's so many different ways of writing this overall conclusion in the context of the problem, but the way that we've been practicing at least is, do you support or not support the claim? Does the data support or not support the claim? The claim being your alternative hypothesis. So we're saying at 5% significance level, the sample data do not support the claim that, what was our alternative hypothesis? This was our alternative hypothesis. So we're not supporting we are not supporting our alternative hypothesis, which was that the distribution of responses is not the same for each gender.
so it's always kind of towards like aiming the alternative hypothesis when it comes to the
Yeah.
conclusion.
And again, technically, there's so many other ways
Yeah, but
that we
that's just
can,
the way-
but I'm just wanting, the way we've been practicing is our conclusion has been always in reference to the alternative. We're supporting our alternative claim or we're not supporting our alternative claim.
Okay. Sounds good.
Yeah, because it's like in research, like that's like this, the whole class is like based on like kind of like a research method. So like in research, one of the first things to do is to like state a claim. You know what I mean? So like that's what we're doing, and like we're like, you know, like testing the claim
Yeah.
to see if it's bogus.
And you'll see, and maybe potentially in your future, wherever you are, you may see other conclusions in the context of the problem where they're referring back to the null, but
So would that
I'm
be-
trying to
would that be
narrow our
incorrect?
focus.
Would
Huh?
that be incorrect if we kind of went towards the null on this question? On, like,
It
the
would
exam?
depend on how it's written.
Okay.
I'll be looking very specifically for how it's written. Yeah.
Fair enough.
Did I say 3 meals a day under?
Yeah.
Okay.
Yeah, 3 meals a day.
Wait,
Because that's the.
I just wrote it. I thought that I was right.
I'm just referencing what the responses was about. The responses was about the 3 meals a day question.
So we can't just bring down our alternative hypothesis.
In this case, you could have, in this specific way I have it written here, if you did not include what I have in parentheses here, I'd be okay with that. but then it depends on how thorough your alternative is here. Okay, right? If your alternative up here, you instead wrote the distribution of outcomes is not the same for each population, and then you wrote that here, outcomes and population, then I'm going to be like, well, what the hell was the problem about? What were the outcomes? What were the populations? And in this case, the outcomes are the responses, and the populations are the gender. Does that make sense?
Would responses though apply to most problems that we would see like this?
No, not necessarily.
Okay. So I had to remember either outcomes or response.
Just if you're concerned, the more thorough, the better. List out what the outcomes are, list out what the populations are.
But are we talking about like the meals per day or the fact that they're male or female?
The meals per day are the outcomes. The populations were the gender.
Alright.
In this case.
To make it easier, like, you know where it says at the 5% level of significance, test the claim that the distribution of population proportion. Can you copy that and just put male, female, and then the meals? So that can make it easier.
Says the claim distribution of population proportions for gender is not the same for each response. So you're copying this for what part? For the alternative?
For the state the conclusion.
For the
Just like
conclusion.
male and female, that it doesn't support it. That's how I see it.
Be careful because this, whatever appears here,
Uh-huh.
it just so happens that what they stated here is not the same. It just so happens to match that that's what the alternative is.
Okay.
That's not always the case.
Okay.
So you want to be careful.
All right.
Because they might say the same, they might say not the same. It just depends on the problem. Regardless, your null will always be same. Your alternative will always be not the same.
Why is that? Like, it's just like on like a rule about that?
Yeah, just so we all have the same foundation starting point.
Mhm.
So we're all starting off just saying they're the same.
Yeah, it's so weird because like when I look at this problem, like what she just read is like at 5% significance level. I think that's like the null hypothesis, and I think that's what they're trying to like test.
Yeah.
So that's why I put that as my null. Like
Yeah, I know. It's a little tricky. So just think this is telling you overall what we're testing, but regardless, null is the same, alternative not the same.
Okay.
Good questions, guys. Any other questions?
No, on the next one, I already have a question.
Okay. Okay. Next question. It gave it away. Didn't mean for that to be like that.
Say it over.
Yeah. What kind of question is this?
Well, plus
I
it's
know
the only one
about.
out of the four that we haven't done yet.
Yeah. That's funny. Okay. A manager would like to determine if there are significant differences in the mean sales among 4 stores. The following table shows the sales in thousands of dollars tracked over 5 days. Test or claim using a significance level of 5%. So it's ANOVA. In case it doesn't say the word ANOVA, like let's pretend that wasn't there, okay? Then how could we identify that this was in fact an ANOVA test? Well, we're working with multiple populations, right? Among 4 stores, 4 separate stores, that's 4 separate populations. And it says, where to go? We want to see if there's significant difference in the mean sales. So mean sales, we're talking about money, right? Which is quantitative, right? Quantitative. Money is a numerical, the measurement, money, numerical, quantitative. This is the money, right? So that's telling us it's ANOVA. ANOVA is the only one we're using for quantitative data, more than one population. So that's how we know it's ANOVA. So, part A. What are the null and alternative hypotheses? Well, the null, again, look back to the toolkit review sheet we did today. Recall that the null is that the means are all equal to each other. How many of them do we have equal to each other?
4.
4, because it's 4 different stores.
I'm having an issue.
Mm-hmm.
Is our population like normally typically going to be on the like the rows part?
Whether it's horizontal or vertical,
Yeah.
it could be either.
Because like that initially when I look at it, that confuses me, like I don't know which,
Yeah.
Good point,
you know,
Good
like,
question.
cause I just did 5, cause I was thinking of the days.
Yeah.
yeah.
So
Oh, yeah.
Keith, yeah. So
I
be
will
careful.
wonder.
So a manager would like to determine if there's a significant difference in mean sales among the 4 stores. So what's the populations? The 4 stores. It could have been across 5 days. It could have been across 5 months. It could have been across 5 years. It could be across. Yeah. But what matters is the populations. What is the population here? The populations are the stores, and we have 4 of them. Okay. And so that's why we have mu1 also equal mu2 equal mu3 equals mu4. We're only doing 4 of them for the 4 stores. And then the alternative, at least one population mean is different. Basically, we're saying one of the ones in our null hypothesis was wrong. So next, using ANOVA on your calculator, find the test statistic F and the p-value. So recall, this is a calculator problem. You go to Stat, Edit, clear out any old data if there is old data. Okay. So this kind of goes to your question I think you're asking to ensure you're entering the correct data. Are we entering in our data horizontally for each store, or do we enter our data in vertically for the days?
Vertically? No?
No.
Would it be like that?
Horizontally for each store, because that's what we're talking about. Our population data is per store.
Wait, what?
So
So we just have.
Alhambra, this is our L1. Oops, I can't read that.
Yeah.
Oh, so it's, oh shoot.
That's L1. And then, I need another color. And then Burbank, that's your L2.
I did it opposite.
Oh, I know what. Okay.
Okay.
I totally
that's-
screwed that up.
Cerritos is your L3. Right? Because it's dependent
I
upon
was doing
the, yeah, you got to think, yeah, so be careful there. The population, what's our populations here? It's the stores. So you keep the data across the stores, not data across the days. Because if you were to do it by the day, like look here, if you do it by the day, notice how you're mixing up the data from all 4 stores, right? Day 2, this is data from store 1, store 2, store 3. You're, like if you do it by the day, you're combining the store's data. We don't want that. These are distinct stores. These are distinct populations. Keep their data separated. So Alhambra is L1, Burbank L2, L3, and then L4. And that goes back to your question, Kristen. The table could have been inverted, right? To where the days and the stores were swapped, in which case then your data is going down vertically. What matters is the population. Okay? So be careful with that, guys. Please be careful with that. Okay, so 10. How come it's not letting me? Try this again. So stat, edit. Guess I'll just do it like this. Okay, so 10, 15, 10.
It never tells where to run.
20. Three, 7. Okay, so you enter in the 4 stores data into L1, L2, L3, L4. Then you do stat. Tests. Go up to ANOVA. All right, go up to ANOVA. These ads. There you go. Okay, so I went up to ANOVA, hit enter. Do we just leave it like that? Do we just leave it as ANOVA?
Second L1.
Good. You have to enter in the lists, right? Yeah, with commas in between. So I'm gonna do second L1, comma, second L2, comma, second L3, comma, second L4. That was the last one. So you end it with parentheses. And it gives you a ton of info. Are we using all of it? No. All this is asking for is the test statistic F and the p-value, which should be the first two things at the top. So F, you should have gotten 35.295. And your p-value, you should have gotten, be careful here. There's an E at the end, which remember that tells you to move the decimal. So I'm actually going to put this here. So the p-value is 2.7665 E negative 7. So that means to move the decimal 7 times to the left. So it's going to become 0.12345 I'm going to round the first digit there.
Wait, why do you round that?
Hmm?
Why do you round the last, or the 3? I mean? What do you round it to the 3?
Because 2.76 is closer
So
to
we
3.
should round before you move the decimal?
Up to you. Up to you. I mean, if you wanted to, you could have just left it like this: 0.00000027665.
Okay.
Either way.
Okay, I see.
Either way, though, if you were to round that to 3 decimal places, because that's usually where we go to, what is it?
0.
A 0. 0.
Wait, so if we left it as all those zeros and then 2, that would be wrong?
No. Well, with 2, yeah.
With 2, that would be like a half point wrong, because that means it wasn't rounded correctly.
Okay.
Because next to the 2 is a 7, which bumps it up to 3.
And then also I have a question. You know how we did in class like MS and...
We're not doing that on the
Okay,
exam.
so it'll just be the F and the P.
Correct.
So that's not on the exam, the MS stuff?
No.
Nice.
Just F and P.
That was the stuff I was stressed out about.
Yeah.
Okay, any other questions here? So our F was 35.295. Our P value is really just 0. Okay. All right, so what conclusions can we make? Well, our P value is basically 0%, which is less than or equal to our level of significance, which we were told was 5%. Making it statistically significant. So we reject the null and support the alternative.
This is so easy to me now. Like, part C, I used to struggle on that so much.
Yeah.
Yeah.
And now it's just like second
Now,
nature.
yeah.
Easy.
Yes, I love hearing that.
Ruined me.
We're like researchers.
You guys got this. Okay, now state the conclusion and context of the problem. At 5% significance level, the sample data support the claim that, and your claim is your alternative, right? Your alternative hypotheses. But be careful, if there's not enough detail here, you need to include the detail in that very final overall conclusion, right? So here we said at least one population mean is different. But what are these population means? What are we talking about?
The cells.
The sales,
among the
right?
4 stores.
Yeah. So basically, the null was saying that the mean sales among the 4 stores are equal, right? That's what the null was saying. The null was saying that the mean sales among the 4 stores are equal. And we're now saying that no, they're not all equal. The mean sales of the 4 stores are not all equal. Or at least one of the mean sales stores is not equal, right?
So at least one of the mean sales of one store is not equal.
Yes,
Or-
something along those lines.
You give them.
Yeah.
Can we use a sentence from the question that says significant differences in the mean sales among 4 stores?
Well, it's not that it's significantly different, because rather the conclusion, or from our null, we were saying that they were equal, right? Our null was saying that they were equal. And we're saying that at least one of them is different. So we're not just saying that there's differences, right? It's not enough to just do that. So I'd prefer something along the lines of support the claim that at least one store has mean sales not equal to the others or different from the others.
What if I put the mean sales in at least one store is different?
The mean sales in at least one store is different. That's fine. If anyone else wants to
What if you say incorrect, that's fine too?
say it in a full sentence for me?
Just at least one store, of the mean sales is incorrect.
Yeah, that
Yeah,
works.
That's what I wrote in my, what's it called, alternative.
Is
too. Like,
incorrect,
instead of
that is.
different, I wrote incorrect, that's, cause I saw that in the homework, so.
Incorrect. Which basically means that they're different. So yeah, I would take that, yeah. Okay, any other questions? Okay, I'm gonna go ahead and stop recording.